two racers on motorcycles, and one of them has a velocity that's given as t squared, and the second racer has a velocity that's given as the square root of 125t. And I've said that both of these are valid really for the first 5 seconds. So the thing is that at t equals 5, these two equations have the same value. So v1 of 5 is equal to v2 of 5. But what that means is that the velocity of the two riders is the same. However, that doesn't mean that they've traveled the same distance. To find how far each of the riders has gone, we're really looking for the area under the curve. So that second part, and I'm not going to finish this off completely, I'm just going to kind of talk through the interpretation piece. So the second part of this question says to give an interpretation of the area between the V1 and V2 curves. Well, the interpretation is that the area between those curves is the distance between the two riders. So if after 5 seconds, the area between the two curves is 0, then they are in the same location. But if after 5 seconds, the area between the curves is not 0, then they are not in the same location. Because I'm not asking about the velocity, I'm asking about the location. Now, the other way to think about that is to think about this in more of a differential equations-y aspect, right? So velocity is the derivative of the position function. So we would need to be looking at the antiderivatives at 5 to figure out whether they were in the same place. Okay, other questions from my practice sets. Set 2, question 2B. I think that was another one that involved words. Oh no, set 2, 2B was a volume problem. So this one, since we haven't done very many volume examples, let's finish off this volume problem. So again, this is from my problem set 2, and this is problem 2B. And the question that I've given us is to consider the region bounded by y equals e to the x, y equals 0, x equals 0, and x equals 1. And what we're going to do is revolve that around the x-axis. So I prefer to do this with a picture, though we can do it without a picture. But y equals e to the x, that's one I know pretty well. Here's y equals e to the x. Here's y equals 0. We're going from x equals 0 to x equals 1. So we're talking about taking this piece and revolving it around the x-axis. In lecture the other day, Professor Chaudhary said that in terms of the test, it's really he's only going to think about volumes revolved around the x-axis. So if you've had 17B in a previous life, or you've taken calculus in a previous life, you might have done some things where we revolved around the y-axis or revolved around a different line. But he's only going to test us on revolving around the x-axis, which means that the formula is really going to be the same every time we do this. So I'm going to have pi times the integral from, in this case, my bounds are x equals 0 to x equals 1. And then I'll need my function squared dx. And this right here is really that pi r squared that's coming from taking our arbitrary cross section and spinning it in a circle, so that our volume becomes the area of that circle times a little bit of thickness. Now this trips some people up, but I'm going to pause for a second to rewrite this, because a power raised to another power, I can multiply those exponents, which would leave me with pi times 0 to 1 e to the 2x dx. And my guess is if you get this far, you can probably finish the integral off, but let's do it together anyway. This comes back to one of those integration basics that we had back in section 4.6. So when I'm integrating e to a constant times x, my answer becomes 1 over that constant times e to the constant times x. I don't want to lose my pi, so I'll go ahead and put it on top. And then we're evaluating from 0 to 1. We already know that we do not have to simplify this. So I'm just going to leave this as pi over 2 e to the 2 minus pi over 2 e to the 0. If you want, you could take the e to the 0 and replace that with a 1. Just kind of catching back up in terms of comments in the chat. So there was a comment referencing back to this problem. And the question is, what if I had given you the acceleration functions instead of the velocity? So if I had given you acceleration functions, then the area under the curve would be talking about velocity. That is true, because the antiderivative of acceleration would go back to velocity. So other questions people wanted to go through on my practice problems included from problem set 2, question 3, and from problem set 1, question 1, which seems like that probably means we would like to talk about some of those limits where our limits of integration head to infinity. So I'm going to erase this one. And we can totally go through some improper integrals. And I don't know if everybody picked up on this, but in lecture last week, Professor Chaudhary talked about that for the improper integrals, the things he really wants you to be able to handle is x raised to some power and e raised to some power. Those are the things that he's really interested in you being able to deal with the like long-term 0 to infinity, 1 to infinity kind of integrals. So let's take a look at my problem set 1, question 1. So practice set 1, problem 1. So in this problem, I have stated that we have a tumor that is growing at a rate of dw dt equal to 5t e to the negative t squared in grams per year, where t is measured in years. So the first question says, how much did the size of the tumor change in the first 2 years? So this really is one of those like interpret a word problem kinds of questions. So this is telling me the rate of growth. And if I want to know the total change in the growth, then we can think about this more of a differential equation, or we can think about it more as an integral. But either way, we'll end up doing the same math. So if I think about this from a differential equation standpoint, this has given me the growth rate. And so if I found a function for the weight at any given time by finding the antiderivative, then that question about how much did it change in the first 2 years would look like what was the weight at year 2 minus what was the weight at year 0. That would be my total change in the first 2 years. And how would I come up with the weight if I had the derivative? Well, I'd take the antiderivative. So putting that all together with our calculus tools, that means we're looking for the integral from 0 to 2 of 5t e to the negative t squared dt for that first question. So looking at this, I'm going to need to find the antiderivative of this. And I'm going to look at that and say, well, we know we're not supposed to need integration by parts. So I guess it's going to have to be a U substitution. So looking at this, I'm trying to answer that question of does the derivative of one part equal the other part? And my answer to that question is yes, almost, kind of, sort of. So I'm going to take that 5 and just move it out of my way by putting it in front of the integral. And then I'm going to do my u substitution. I will let u be equal to negative t squared. That's going to make my differential negative 2t dt. I don't have that negative 2t, but I do have the t and the dt. So I'll rearrange that to say negative 1/2 du is equal to t dt. Now I've got almost everything I need in my vocabulary list, but I haven't yet dealt with the bounds. So I'm going to choose to change the 0 and the 2. So I'm going to come over here and say when t equals 0, u would be equal to negative 0 squared, which is 0. And when t is equal to 2, then u would be equal to negative 2 squared, or negative 4. That means that when I write this and I translate it, I'd have the 5, I'd have the negative 1/2. So I'll put all of that in front. My bounds, and this one's a little bit tricky, but I need to keep the bounds in the same place. Since t equals 0 was on the bottom, I'm going to keep 0 on the bottom here for the u. Because t equals 2 is on the top, I'm going to have u equals negative 4 on the top. E to the u du. You have a choice to make here. If it makes you uncomfortable to have the negative 4 on top and the 0 on the bottom, you can always use that rule that integrating in the opposite direction pops out a negative in front. But I'm just going to go with the way it's written here. The antiderivative of e to the u is e to the u, which means I'm going to end up with negative 5/2 e to the u evaluated from 0 to negative 4. That means I'm plugging in the negative 4 first. So I'll have negative 5/2 e to the negative 4 minus negative 5/2 e to the 0. And we don't have to simplify. We can walk away and just leave it like that. Part B of the problem asks us, if the tumor continues to grow for a very long time, what mass is it going to approach? So I'm actually not going to erase anything. So I'm not going to erase anything just yet because I'm letting some questions pop up, but then I'll move on to part B. So we have so the one is the issue about the negative. The negative is essentially going to correct itself as long as we plug them in as the top minus the bottom. But if you don't like that, you don't have to do that. You have two other options. So one other option is to say that, I'm going to get rid of this grams per year for a second. But one of the other options is to say that any integral from 0 to negative 4 of f of t dt is equal to the negative of the integral from negative 4 to 0 of f of t dt. And that's one of our properties of definite integrals, which means that from here, we could have written it as positive 5/2 and the integral from negative 4 to 0 of e to the u du. Now, if we had done this, then we would end up with 5/2 e to the 0 minus 5/2 e to the negative 4. But notice these are the same, right? As long as we do this in the correct order, the minus signs are going to correct themselves. We'll have a positive 5/2 and a negative 5/2 e to the negative 4th. So they're going to match. You can make the pick. The other option, which someone brought up, is do you even have to change the endpoints? So you don't have to change the endpoints as long as you plug back in at the end. So the other option would be to not write this as 0 and -4, but to leave it in the values from t and then plug back in at the end. Other questions that I'm seeing in the chat. One, just be careful because notation wise, this says square the t first and then make your answer negative. If I wanted it to be the other way, it would have to look like -t squared. Okay. I think I've addressed most of the questions in there, and cool. Now I lost my train of thought. That's okay. So for part B, we're essentially, everything about this problem is the same, but instead of being a 2, we'd have an infinity up there. So I would go ahead and put that infinity in. Nothing would change about the rest of the problem. And I do see a couple questions in the chat, and I'm not ignoring this. There seems to be a lot. There are like 5 of you that are trying to get me to not do this, or suggesting that we could choose to not do this. And questions about when should you do this. So here's the bottom line. Every time I do a U substitution, if I have a definite integral, personally, I'm going to change the bounds. Mathematically, that's the most mathematically rigorous option. However, Professor Chaudhary has said that it's fine for you to not change the bounds when you do the substitution, as long as you plug back in for U at the end. So in terms of, is there a situation where personally I would choose to do it that way? No, I'm going to choose to change the bounds. But if you would like to see it the other way, here's what that other way would look like. And I'm going to hold on to this answer just to show that no matter how we do it, we're always ending up at this same place. So if I chose not to change those bounds, then over here, I'm going to write for myself t equals 0 and t equals 2. And I'm doing that to remind myself I have to plug back in what t was. So if I do it this way, then I'll end up with -5/2 e to the u, but I'll have to turn that into -5/2 e to the -t squared, and then plug in 0 to 2. So I'll still end up in the same place, -5/2 e to the -4 minus -5/2 e to the 0. Do whatever is going to work best for you. I'm always concerned that I'm going to forget to plug back in. So for me, if I'm translating stuff to U, I'm going to translate the entire integral to be in terms of U. Okay. I think I've addressed most of the questions. So there is one lingering question that is asking about, will the word problems always involve some kind of derivative? And I have 2 answers to that, right? So in terms of the stuff that we're likely to see on this exam, I do think we're likely to see a test question that does involve some sort of derivative-y problem. However, it might not be written to say dw dt. So for example, for this problem, I could have just said in words that the tumor is growing at a rate of, and given you this equation. And some of the problems in the book do that. So they don't explicitly write a derivative. They just say something in words that means it's a derivative. So at a rate of, increasing at a rate of, those are words that are telling us this thing, this equation is a derivative. The other case where this happens is when they've told us it's a velocity. And if they've told us it's a velocity, we have to know that was the derivative of the position function. So hopefully that makes sense. And then in terms of how I dealt with the constant, that is totally up to you. If you prefer to have the constant sitting right here next to the e to the u, that's totally fine. It wouldn't change anything about the problem. Whether I write that as -1/2 times 5, or I write that as -5/2, either way, it's the same number. So no, it doesn't matter whether you've pulled the 5 out or not. And it seems like there's a lingering question about where the 5 came from. It's part of the original question. So this is the original function that I gave us for dw dt. So that's where the 5 came from. It's just part of the problem. Yeah. Okay. I think I've gotten through all the questions in there. So I do want to go ahead and do I do want to do the second part of this, which is if it grows for a very long time, what will the weight be? So after a very long time, and since I've already got it written out this way, I'm just going to keep going with the way it's written out. So after a very long time, that would mean t is headed to infinity. And when we have an improper integral like that, it means we're going to rewrite it to say the limit. We'll pick a letter. It doesn't matter what letter. I'm picking B. And we're going to let that letter go to infinity. So if I jump over to here, we'll squeeze in the limit as B approaches infinity. And instead of a 2 up here, I'm going to have a B, which means we'll end up with a limit as B approaches infinity. And plugging that in, I've got -5/2 e to the negative b squared minus -5/2 e to the 0. So here I'm going to think through, if I plug in infinity, infinity squared is infinity, but then it's a negative, and e to the negative infinity is going to 0. So this would look like 0 plus 5/2. So after a very long time, we're expecting that tumor to be about 2.5 grams. Okay. It's about 10:27, and like I said, Friday can be review also. I've also got office hours tomorrow, so we can keep doing problems. There is a request, right, to go and look at problem set 2, question 3, which is going to get us 2 more practice problems with these infinite limit bounds. So let's move on to take a look at those. And I don't know if you noticed, but I feel like I wrote harder practice tests this time than the first time. I think that my practice tests are probably more difficult than what you will see on Friday, but that's always my goal. You should practice for something more difficult, and then hopefully when you walk in, what you see will feel a little friendlier. So problem set 2, problem 3. And so there are 2 parts to this one. My first question goes 1 to infinity, 1 over the square root of x dx. And so first of all, right off the bat, as soon as I see that infinity, I know that I need to rewrite this with a limit. So I'll rewrite that to say the limit as b approaches infinity, 1 to b. And I'm going to go ahead and take the time to rewrite this to say x to the negative 1/2 power. There's nothing fancy that I have to do with this. This is one of our basic integrals because we have x raised to a number. So with x raised to a number, I'll add 1 to the exponent, which is going to give me x to the positive 1/2, and divide by that new exponent. Again, we're going from 1 to b, but we want to make sure to keep writing that limit. We could choose, I'm going to choose to rewrite that on my next line here while I plug in the b. So dividing by 1/2, that's the same as multiplying by 2. And x to the 1/2, that's the same as the square root of x. So I'm going to write this as 2 square root of b minus 2 square root of 1. If I take the limit as b approaches infinity, the square root of infinity is headed to infinity. So we want to make sure that we write that it diverges. For 3b, hopefully you saw my note yesterday that I changed the problem. It was really terrible before. I started to write solutions and I was like, oh man, this is like a crazy Dedel practice midterm kind of problem. This is not appropriate. So I've got x, natural log of x cubed dx. Right off the bat, I know that I've got that infinity in there, so I'm going to have to switch this around to have a limit. And I think I'm going to need all the space, so I'm just going to squeeze it in and squeeze in my limit as b approaches infinity and stick an infinity up there. Well, this time, when I go to integrate, I am looking at something that's more complicated. So we are not going to need integration by parts on this test. It must be a U substitution, which also just reminded me somewhere in the chat, someone had asked about ILATE, and you will need that for the web work homework, but you will not need that for the test. There is no integration by parts on the test. Section 5.5 is not on the test. Okay, so if you see something complicated, you know it's a U substitution. The question you have to ask yourself is whose derivative is hiding in there? And in this case, it's the derivative of natural log of x. I'm going to come off to the side and let u be equal to natural log of x, which makes du 1 over x dx, which I've got. I've got the 1 over x, and I've got the dx part. So the only other thing that I need to do is translate my limits. And I realized I wrote the infinity over there, but I forgot to call it b over here. So I'm going to come off to the side and say when x equals e, u would be natural log of e or 1. And then when x equals b, u would be equal to the natural log of b. That's all we're going to do. We're just going to leave it right like that. So I've got the limit as b approaches infinity, and my bounds become 1 and natural log of b. The function we have in here is 1 over u cubed du. And I'm going to write that 1 over u cubed as u to the negative 3rd power. Now I'm ready to find that antiderivative by adding 1 to the exponent, getting u to the negative 2, and then dividing by that new exponent. We're going to take that from 1 to natural log of b, and then take the limit as b approaches infinity. We've got the limit as b approaches infinity. And if I didn't have to take the limit on this, I would probably leave it looking like this. But for me, it's easier to see what's happening in the limit if I take that u to the negative 2 and I actually move it back down to the denominator. So when I plug in that ln of b, I'm going to plug it in, but I'm going to have this say -1 over 2 ln of b squared minus -1 over 2 times 1 squared. For me, that makes it easier to see what's happening in the limit. So if I take the limit as b approaches infinity, natural log of infinity is infinite, and then I'm squaring that, so it's even bigger. And now I've got 1 divided by a huge number. Well, that is going to 0. Minus a minus is going to make that plus a 1/2. And just for good measure, I will go ahead and write that it converges. Amazingly, I saw 0 questions come up in the chat as I was working through that. Juan, you have a question?
Okay, so I understand we use u substitution when there's something that's the derivative of it. Like we have ln of x and we have 1 of x. Is there a way to maybe like split the 1 over x and ln of x so that I can maybe see it? Because it's like, so I can maybe like visualize.
Yeah, so the fraction there, we can certainly break apart, right? So 1 over x times natural log of x cubed, just in terms of dealing with fractions, I can write that as 1 over x times 1 over natural log of x cubed. I don't know if that helps visually.
Yeah, it does help. Okay, now I understand why it's u to the -3. Could I, let me take a screenshot real quick.
Yeah, for sure. Okay, so there's a question saying, I think I understand what the question is, and I think the question is again referring to the fact that I switched the bounds around. Oh no, it's the fact that I said to evaluate. Yes, okay. So there was a problem. I can't remember if it said textbook problem or a worksheet problem that just asks you to rewrite the integral using a limit, in which case it's not asking you to evaluate. This one is asking us to evaluate it or show that it diverges. So that means we got to do the whole thing. We got to rewrite it with the limits, but then we also have to actually work through the integral. Yeah. Okay. So I think that I've made it through all the requested stuff from the practice test. I'm going to go scroll way back up to the beginning of the session because I had there were a couple of questions to go over specific textbook problems that I want to make sure that we take a look at. So I am headed to page 362 and looking at problem 65. And it's a bunch of words, but let me go ahead and share my screen really quick. And are we seeing, hopefully we're seeing question 63, and actually the question was question 65, I'm realizing, so cool. There aren't a whole bunch of words. I'm going to stop sharing. I was looking at the wrong question. Okay. So this is actually a really great question, and I could totally see it being a test question, actually. So the question says, if f is continuous, and we know that the integral from 0 to 4 of f of x dx is equal to 10. We need to find the integral from 0 to 2 of f of 2x dx. This is honestly a super excellent test question. So if you haven't taken a look at this, let's take a look at it now. Well, this right here, the choice of the letter x is completely arbitrary. This integral would be exactly the same integral if I chose to write this saying 0 to 4 of f of t dt. Or if I made it say 0 to 4 of f of u du. And we're going to exploit this fact to manage this. So this equation doesn't say f of 2x, it says f of x, or f of t, or f of u. So I'm going to need to do a u substitution here. I'm going to let u be equal to 2x. Well, when I do that, I'm going to do the same thing we're doing with any other u substitution problem. I'm going to build my vocabulary list and translate the question. So to build my vocabulary list, du would be equal to 2 dx. That means 1/2 du is equal to dx. The other thing that I have to translate, and I don't have a choice, you must translate those limits of integration. I have to translate the 0 and the 2. So I'm going to come off to the side and say when x equals 0, u is equal to 2 times 0, or 0. And when x is equal to 2, u is equal to 2 times 2, or 4. Well, what that means is when we translate this, my limits have now changed from 0 to 2 to 0 to 4. This part becomes f of u, and dx becomes 1/2 of du. Because this choice of letters was completely arbitrary, this is equal to 10. And the final answer here would be 5. Now, the reason that I said that this is actually a really good test question is this question gets at the heart of, do you understand what's happening with a u substitution and the process that you have to do? But it isn't mathematically complicated to evaluate or to find that. In fact, we don't ever have to actually find the antiderivative. Juan, you have a question?
Yeah, I noticed that on the web works, I didn't need to like say when x equals 0, u is equal to this for some reason. So I'm just want to know, when do we use the u substitute? When do we find the new bounds or find the u bounds, if that makes sense?
Yeah, so if you have a function, right, like if you explicitly know what the function is and you're going to take the antiderivative of it, you always have the option to plug back in the values at the end. That isn't the way that I do the problems, but you have the option to do that. The issue is that here, because we don't actually have a function to find the antiderivative of, we don't have that as an option. We have to switch the bounds. Now, there are also problems, and I didn't check all of the web work problems, but if there aren't bounds on the integral, right, if it's an indefinite integral and we're doing u substitution, then we're never changing bounds. The other time that we wouldn't be changing bounds is something like, for example, if I wrote a problem where we were integrating from 0 to 1, but the u substitution was that u was equal to x squared. 0 squared happens to be 0 and 1 squared happens to be 1. So even if you didn't change the bounds, you would accidentally get the right answer. So my guess is that on the web work, if you didn't find yourself having to do this, one of three things happened. They were indefinite integrals, so they didn't have bounds, or accidentally the bounds worked out, or you plugged back in what the x's were before plugging stuff in at the end.
So I think like, yeah, because I don't think I had to plug in the u bound or like become like get the u bounds because I just plugged in the formula x. Like I just
Correct. But in this case, that wouldn't work. You literally would not be able to get an answer if you didn't change the bounds. So my advice is that it should always work to change the bounds. So I would rather choose to do the thing that I know will always work.
Could you give one more example of where we would have to change the u bound to?
For sure, like write something kind of like this. I'll just pick another one from the textbook because I think there were like 2 or 3 in that same section. So I'm in that same section, so I'm on page 362, and I'm on page 362, and I'm going to do number 64. And number 64 says the f of x is continuous, and we're going from 0 to 9 of f of x dx. That's equal to 4. And the thing we need to find is the integral from 0 to 3 of x times f of x squared dx. So again, the first thing that I want to recognize is that in this definite integral, the choice of letter is arbitrary. It could be an S, it could be a T, it could be a U. So this would be the same as writing 0 to 9 of f of u du, which would also be equal to 4. So when I come down here to evaluate this problem, well, this definitely, I don't have a function. I'm going to have to find a way to make it look like this. And the only way to do that is to sort of come off to the side, and I'm going to let u be equal to x squared. Well, if u is equal to x squared, then my differential du would be equal to 2x dx, which we don't have in the problem, but we have the x dx part. So this would become 1/2 of du is equal to x dx. And then because I have bounds, so anytime I'm doing a u substitution and I have limits of integration, I'm going to change them. So I'm going to come off to the side and say when x equals 0, u is equal to 0 squared, or 0. And when x is equal to 3, u would be equal to 3 squared, which is 9. So I'm going to rewrite this. We're going to have 0 to 9. The x dx becomes 1/2 du. And I choose to put my constants out in front. It's not a problem at all if you want to put it inside. And then f of x squared becomes f of u. And now this integral, we've been told, has a value of 4. So my final answer there would be 2. And Juan, I can't tell if your hand is still up because you have another question. No, put your hand down. Okay, cool. So there's a question about translating from this to this, and it comes from, I really liked it in the old textbook. They actually did this, and they would write it as, they wrote it as our UX dictionary. So this is like my translation sheet. So I have to translate everything in this problem into something with u's. So the f of x squared, since I made x squared u, I'm going to have way too many colors going on, but that f of x squared piece turns into f of u because x squared gets replaced with u. At the same time, that x and dx term, the x and the dx come together and they're almost equal to du, but they're actually equal to 1/2 du. And I stuck my 1/2 out in front. But that's what's happening with the different pieces.